Assalamualaikum warahmatullahi wabarakatuh. To Dr. Juliana Ibrahim. Today our group want to present our case study about the topic tunnel construction of sequential excavation method. First of all, I will introduce my team's member. First, Muhammad Syafirul Syafiq. Second, Muhammad Zulfikri. And last, Siti Liana Hadir. First, let me present first about project detail. From this slide, we can see a map showing the railway tracks. It has 3 sections of them, and let me tell you the method used according to section. Okay, first section A, that use sequential excavation method. Second, section B, use tunnel boring machine TBM and drill and blasting. The third is section C, use sequential excavation method SEM and open cut method. Okay, now I will talk about our case study. The project title is East Coast Railing, ECRL, and person in charge is Muhammad Izzat bin Muhammad Ramli. His position is engineer, and site location is at Serendah, Selangor, Malaysia. And it always called section 8 because it has a total of 21 panel under this project. Okay, for the purpose to alleviate traffic congestion and improve public transport connectivity and specification of length, as this tunnel have 2 tunnel, and first tunnel the length is 3.5 km and the second tunnel is 9.85 km. And the timeline for this project is construction began in January 2016, but the project started to progress slowly due to the COVID-19 pandemic and resume normal operation in 2022. Expected to be completed in January 2027. Okay, for the client, the client is Malaysia Railing, Sdn Bhd is MRL, and the contractor is China Communication Construction, Sdn Bhd is CCC. And historical context, the area has seen significant urban growth, necessitating new transport solution, and environmental consideration is initial assessment indicated the need for measure to protect local wildlife, and less regulatory framework is compliance with local and national construction regulations. Okay, and excavation method for this SEM has 2 bench cut. First, 2 bench cut for normal rock and 3 bench cut for weaker zone. Okay, for the lining and design headline, the composite lining with fire and water resistant. Second is P10 waterproofing grade, and last adapted SEM method depending on tunnel zone. Okay.
For this section of our group presentation, I will focus on the one of tunnel construction method used in ECRL project, the Sequential Excavation Method or SEM, also known as the New Australian Tunnelling Method and ATM. This method is chosen mainly for short tunnel and highly efficient in terms of time and cost compared to tunnel boring machine TBM. It allows the tunnel to be excavated by segment, which means smaller construction footprint and better adaptability to difficult soil conditions. This approach is ideal for forested or mountain areas like those the ECRL alignment. One of the key advantage is that it also includes a waterproofing process, which is crucial in preventing water ingress and maintaining tunnel integrity over time. Okay, now let's look at the step-by-step process involved in SEM. First, the tunnel is divided to segment to control the excavation. Then, each segment is excavated carefully using machine like road header or even blasting, depending on the soil and rock condition. After excavation, the shotcrete, which is high-pressure spray concrete, is applied to stabilize the exposed area. Rock bolts are inserted to reinforce the ground and prevent collapse. Next, reinforcement is installed such as steel mesh and rib support. Next, waterproofing membrane is added to protect the structure from groundwater. Finally, the lining and track bed concrete are applied using specialized rolling. This sequential and layered approach ensure both structural stability and environmental safety. Here, we can see 2 important elements in SEM tunnel construction. The first picture is tunnel lining foam boot trolley is used to pour the secondary concrete lining smoothly and efficiently. Okay, the second picture is the waterproofing membrane is applied before the final lining, acting like a shield that protects the tunnel structure from water damage and reduce maintenance costs in future. These tools reflect the integration of advanced technology in tunnel construction, helping us achieve precision and durability. Okay, first of all, refer to the picture on the slide. The normal numbering is for excavation process and the Roman numbering is for concreting process. Okay, let's take a closer look at the 2 bench cut method, which is one of the excavation sequences used within the Sequential Excavation Method SEM. This method is applied when the tunnel size or ground condition make it impractical to excavate the full face in one go. So, the tunnel face is divided vertically into two benches, an upper bench and a lower bench, which are excavated one after the other. Here, how it works step by step. First, they excavate part 1, which is the upper section of the tunnel face, and immediately apply primary support using shotcrete and reinforcement. Then, they move to the part 3, the lower bench, and repeat the support process. After that, the invert or part 5 is excavated. This step is done in short length of less than 3 meters to ensure stability. Then, they put the invert base part 6 and do the bottom filling part 7. Finally, using a lining trolley, they pour the secondary concrete lining part 8 in one continuous operation. This sequence is still under SEM, but it's practically used in tunnel with larger cross-section or poor soil conditions, where full-face excavation might risk collapse. By adjusting the excavation process, engineer can ensure safety while maintaining efficiency. Another great example of the how SEM adapt to geological challenges.
Alright, let's move to the 3-bench method. In this method, the tunnel face is divided into 3 horizontal sections or benches, which is the top, the middle, and the lower parts. The process begins with part 1, the top bench. This section is excavated first, then anchor bolts are installed and shotcrete is applied as primary support. Second is part 2, the middle bench. After excavation, steel ribs are extended downward from the top bench, and primary support continues. Then comes for part 3, the lower bench. The same process is repeated, extending steel ribs and applying shotcrete for stability. And once all the 3 benches are completed, part 4, the invert, is excavated. This section is kept short, less than 3 meters, and the supporting is close to ensure full structural integrity. For the base, part 5 and 6, the bottom slab is cast in 2 stages after the invert is properly supported. And finally, the lining template is installed, and the final concrete lining is cast in part 7, often using a trolley formwork system to ensure precision and efficiency. This slide shows the main equipment used in this project. First is hydraulic excavators. They are used first to dig out soil and soft rock, especially in the top and the middle benches. Second, in harder ground, they use the rock header machine. It cuts through rock without blasting, which is safer in sensitive areas. And the third one is crawler truck, carry the excavated material out of the tunnel. It moves easily on good ground inside the tunnel. And then after digging, shotcrete spray machine are used to spray concrete on the tunnel walls for support and safety. And grouting equipment is used to fill gaps and stop water from coming in. This is important in areas with limestone or loose ground. And the last one is tunnel transport system, like conveyor belts or rail carts are used to remove the material faster and avoid delays. So this slide shows 2 main problems faced during this project. The first one is groundwater management, which is groundwater problem. One big issue was groundwater problem, especially from natural springs that were only found after digging started. Even with early surveys, groundwater is hard to predict. It caused delays and made the tunnel face less stable. Second is weak ground condition. Another challenge was the soft and weak ground. The rocks were not very strong, and the tunnel didn't have much support from the surface above. So I show some of the advanced method and tools used by the contractor to make tunnel work safer and more efficient. First, geological prediction. Before digging, the team used survey to check the ground condition ahead. This helped them to prepare for weak rocks or water problems. Second is monitoring system. While digging, they use sensor and regular checks to watch for any movement. This helped them fix problems early before they become dangerous. The third one is smooth blasting. To avoid breaking too much rock, they use a method called smooth blasting. It gave the tunnel a cleaner shape and made it easier to support with board and steel. Right after excavation, they added board, steel frames, beams, and steel ribs to keep the tunnel stable and prevent collapse. And pipe roof support. which is canopy tube. In very soft ground, they install steel pipes in front of the tunnel face. This pipe act like a roof to protect the tunnel during digging. Shotcrete spread concrete. They spread concrete onto the tunnel walls. It dried fast and added strong support like right away. And then primary and advanced support. Basic support like bolt and shotcrete was added right after digging. In risky areas, they also use extra method like canopy tubes for added strength. And then the last one is pre-grouting. Before digging in loose or wet ground, they injecting grout, which is cement mix, into the soil to block water and make the ground stronger.
In conclusion, I believe sequential excavation method, or also we know as NETM, is a smart and flexible approach to tunnel construction, especially in soft or unstable ground like we have in Malaysia. It utilizes real-time monitoring and the ground itself for support, which significantly enhance safety. Despite challenges such as with soil or water issue, SEM remain effective due to its advanced technology and adaptable methods like the 2-bench cut and 3-bench cut technicals. It's not only safe, efficient and environmentally friendly, but it can also adapt to various soil conditions. Plus, it has been proven successful in projects like the ECRL, combining smart design, safety and monitoring seamlessly.